Good day, everyone. I am General and Maranga, together with my partner Blaise Colarte. Today, we will present our mathematical investigation entitled Exploring the Relationship Between Area and Perimeter. In this investigation, we explored how shapes with the same perimeter can have different areas and identified patterns through mathematical reasoning. Let us begin. Allow me to present and introduce to you our learning objectives. For our learning objectives, at the end of the presentation, we should be able to first is explain the relationship between area and perimeter using examples. Second, analyze and verify patterns in rectangles with fixed perimeter. And the last one is formulate and justify a general rule about maximum area. Here are the topics that will be discussed throughout the investigation. So for our table of contents, first is introduction, followed by statement of the problem, investigation process, specialization, conjecturing, justification, generalization, summary and conclusion, possible extensions, and last, references. This investigation examines how a fixed boundary called the perimeter affects the amount of enclosed space known as the area. Through this study, we explore how shapes with the same perimeter can have different areas and identify patterns using mathematical reasoning. A very common belief states that if the perimeter is fixed, then the area is also fixed. Many people assume that once the boundary length is set, the space inside cannot change. However, this idea is actually incorrect, and our investigation will prove that area can vary significantly even when the perimeter remains exactly the same. This topic is highly important because it has practical applications in architecture, construction, and design. It teaches us how to maximize available space efficiently while using only a limited amount of materials. Furthermore, this study connects directly to the isoperimeter principle, a fundamental mathematical concept that explains the relationship between the area and perimeter shapes. The main objective of this investigation is to analyze and understand how the area of a rectangle changes or behaves when its perimeter is kept constant or fixed. We aim to identify exactly how changing the length and width affects the total space enclosed by the shape. We seek to answer four research questions. So our research questions: first, how do dimensions affect the area? Second, can rectangles with the same perimeter have different areas? Third, what dimensions produce the maximum area? And last, what general rule can be formed? Next, we followed four systematic steps in our research. First, specialization, where we examine specific examples and measure different rectangles. Second, conjecturing, where we observe results and identify patterns between dimensions and area. Third, justification, where we use mathematical formulas and proofs to verify our observations. And lastly, generalization, where we form a universal rule that applies to all rectangles under fixed perimeter. In this part, we examine specific examples by keeping the perimeter fixed at 20 units. We list different pairs of length, which are 9, 8, 7, 6, and 5, and width are 1, 2, 3, 4, and 5. Compute the perimeter using the formula 2 length plus 2 width, and calculate the area using length times width. As shown in the table, while all rectangles have the same perimeter of 20, their areas are different. From 9, 16, 21, 24 up to 25, this clearly shows that even with a fixed perimeter, changing the dimensions results in different enclosed spaces. We also observe that as the length and width get closer to each other, the area becomes larger, and it reaches the highest value when both sides are equal, meaning forming a square.
In this slide, we present the data collected from our specialization phase. By observing the relationship between dimension and area for a fixed perimeter of 20, we noticed a clear trend. As the difference between the length and the width decreases, the area increases. For example, when the dimensions are 9 by 1, a difference of 8, the area is 9. However, when they are 6 by 4, a difference of 2, the area jumps to 24. This suggests that the closer the rectangle is to being balanced or equilateral, the more space it encloses. Based on our observations, we formulate our conjecture. For any fixed perimeter, the rectangle that yields the maximum area in a square, where length is equals to width, mathematically, this means that if we are given a constant P, the area A is maximized specifically when L and width are equal P over 4. To ensure our conjecture wasn't just a coincidence for perimeter equals 20, we perform verification using other perimeters like P is equals to 24 and P is equals to 30. For perimeter equals to 24, a 6 by 6 square or an area of 36 still beat a 10 by 2 rectangle A equals 20. This consistent result across multiple test cases strengthens our hypothesis that the square is the optimal shape for area maximization. Now, let's translate this into a mathematical model. We know that the perimeter of rectangle is the sum of all sides, 2 length plus 2 width. To find a relationship, we solve for width. We will move 2L to the other side in order for us to get the width, which gives us 2W equals P minus 2L. And then divide both sides by 2. We'll get W equals P over 2 minus L. When we substitute this into our area formula, which is L times width, we get our area function AL equals P over 2 minus L squared. Notice that this is a quadratic equation. Because the term is negative, we know the graph of this function is a parabola that opens downward, meaning it must have a single highest point or maximum. Plugging in our values, we find L is equals P over 4. Since our width is equals to P over 2 minus L, then width also equals P over 4. Therefore, L equals W, proving that the rectangle must be a square to maximize area. Our generalization summarizes the universal truth discovered. Balanced dimensions maximizes space. Regardless of the size of the perimeter, the geometric relationship remains constant. The more square-like the rectangle is, the greater the area. This principle proves that while perimeter is fixed, the area is dynamic and highly dependent on the ratio of the sides. In conclusion, we have confirmed that perimeter and area are independent quantities. One does not dictate the other. While many people believe a fixed boundary means a fixed space, our investigation proves that the square is the unique rectangle that maximizes area for any given perimeter. This conclusion is supported not just by our numerical data, but by the algebraic proof of the quadratic area function. For future study, this investigation could be extended by exploring 3D geometric relationships such as finding the maximum volume for fixed surface area. We could also compare rectangles to other polygons or circles to see if the isoperimetric principle, it is where the circle maximizes area for any closed loop, holds through as the number of sides increases. That ends our mathematical investigation video. I hope you learned something. Once again, I am Glaze Colarte and my partner is General Maranga. Thanks for watching.